Hello, Python Web Conference folks. We have written a web application. Now what? Of course, you're going to release it to production. But before that, let's learn about the things you'd want to think about. My name is Amit Saha. And in this talk, we are going to learn about strategies to make your services failure ready, whether your service is a monolith or just another service in your microservice architecture. A little bit about me. I started my career as a software engineer, then gravitated into infrastructure-focused engineering roles, and I'm currently a site reliability engineer at Atlassian in Sydney. I collaborate with product teams to improve the production readiness of services. I'm the author of a couple of books. Doing Math with Python is my most popular book so far. And I have a blog at ecorand.me. Let's get started. So this talk is divided into two parts. First, we'll talk about observability of your applications. There are a few definitions of observability around if you go and search for it. My version is if you had to poke your application, not literally, of course, there will be something somewhere telling you if there's something that's rotten in your application. Bad joke, I guess I get it. But you get the idea. We'll focus on this part for most of the talk. The second part will focus on things such as using metrics to implement auto-scaling, running chaos engineering experiments, and a couple of other bits. You may already know these topics, and your applications are already equipped with this, which is great. Today, I'm hoping to summarize all this in a version I would want from myself when I was getting started in these things around 6 years back. Let's get started. So we need a demo service architecture, and this is the architecture that we'll be referring to during the course of our presentation today. We have two services, 1 and 2. They're written using Flask. We have a MySQL database, service and service to communicate over HTTP, and it's service to communicate with MySQL database to make a simple query. We are using the request library for making HTTP requests, and for MySQL, we're using the MySQL connector. All of these are running in Docker containers. The repository here that you see has all the resources that we'll be referring to in the demo. Of course, they're not production ready. There may be bugs. I'm sure there will be bugs. Feel free to send me a pull request or just let me know if I can do things better. But hopefully, this talk, along with the demo resources, will help you explore the areas that we'll be learning about today. So first up, we have observability. I have this bit application instrumentation in brackets, and that's because when we talk about observability, a lot of it is implemented by instrumenting our applications. If you're not familiar with the term instrumentation for your application, if you've ever written a log.info, a log.debug, you are instrumenting your application. Or a print, to help with your debugging, that's instrumentation. That's generally the idea of instrumenting an application. First up, we have logging. I'm sure you're already doing this, but I want to start by referring to a specific format for logging, which is usually called structured logging, or more simply called JSON format, JSON logging. And the idea is instead of unstructured lines emitting from application, you emit JSON formatted strings as lines, which means your logs automatically become searchable and indexable and even graphable quite easily. It's easy for any log processing software to understand JSON formatted log lines. Configure it for your web framework, whether you're using Flask, whether you're using Django, you should definitely configure your web framework to emit JSON formatted logs, configure it for your WSGI runtime. Unicorn, UWSGI both support that. I recommend this library, Python JSON Logger. I have been using this library on and off and have had very good success with using this in production software. Very easy to plug in to your framework, to the runtime. So I highly recommend that. Related to the idea of structured logging, I want to talk about this specific technique of logging, which is called correlated request or error logging. If you search on the interwebs, you will find, you'll probably find exactly what I'm talking about here, but you may find something else. But this is how I understand correlated request or / error logging as. So every time you get a request in your service, you associate it with an unique ID. It could be an UUID that you generate. Then from then on, every time you log anything, a message like a debug message, an error, an expected error, or an unexpected exception, you always log this ID with anything else that you log. So the idea is that all these logs and errors and exceptions all have this unique identifier. When you combine this with structured logging, you automatically can then search for all logs corresponding to a particular request just using this ID. And the third point I want to make is, once you have that ID, propagate that request ID to any upstream service calls. It could be a HTTP service call. It could be RPC service call. You must propagate it. You could even put it as a comment in your SQL query so that you could have that trace from the request to the database. It's super useful in microservices, service-oriented architecture, speaking from personal experience. So this is how we do it. This is an example of using a Flask middleware. You can see this before request that you have that you use to plug in this middleware function. So what we do is we have this get or set request ID. Now, as you can imagine, today it's very rare that your application is going to be directly exposed to the internet. Even if it's, well, let's just accept the fact that a Flask server or for that matter, a Django server isn't really production ready. But even if it were, you wouldn't be exposing it directly. You would usually have a load balancer, either a cloud load balancer or Nginx instance or another some kind of a reverse proxy server running in front of the application. Now, a lot of these load balancers, cloud load balancers such as AWS ALB, already set a header when a request comes in. I know ALB uses this Express ID HTTP header. So if you, in your application, when your application gets a request, when you already have this identifier, you can just reuse it instead of generating a new one. And the advantage for that is you have you're able to trial this request from right from where it entered your infrastructure, so to say. So essentially the idea is you look for any of these known headers. If you find one, use that. Else, you generate a new one using UUID library. And once you get that, you just set it up in your request context. If you're not familiar with Flask, in Flask, the request is a global object, which is essentially a way to store any contextual data in it. So it already has a bunch of stuff in there, and you can stick on any of your custom stuff. So we stick the request ID to this request object here. And then this is an example from the JSON logger I mentioned before. But I believe if you have to use a different logging package, you probably would be able to do something like this, which is you automatically add this request ID field to all log records if it doesn't have one. So every time you try to log, this intercepts that log record and ensures that it always has this request ID field, and it catches from request object. And of course, and then the other, coming back to the third point, which is, so let's say you're making a service HTTP request to service 2, which is referring back to the architecture we started off with. You attach that as a header to that service. So when service 2 decides to look for this request ID header, it automatically finds that and just uses that in any of its logs instead of generating a new one, because that would be pretty dumb, I want to say. It would defeat the purpose of request ID if you're generating a request ID for every service for the same request. So that's the idea. Now, you may be not using HTTP services. Maybe you're using a gRPC service or other RPC frameworks such as Thrift. In that case, you'd essentially stick this request ID into. Now, if I recall vaguely, gRPC has an option dedicated metadata object where you can propagate such metadata. For other RPC services, you may need to add a dedicated field to have this identifier. But yeah, the summary is you'd need to find a way to propagate this request ID to all your downstream services. And then as a result of this, what you have is we have logs like this, which is, say, service 2 logged this with this request ID, and service 1 logged this with this request ID. And you can see they're the same request IDs. So, and coming back to that point again, if you put it into, if you are sending these logs, and it's not a if, you should be sending these logs to a centralized log storage indexing system, you could then plug in this ID and you would have all the logs related to this particular request. And then, of course, a pretty crucial bit of it is you also send this request ID back along with your response. Just all your response will have this X request ID header, which means when a user gets an unexpected error like a 500, they will get back this in their response, especially if it's a reproducible error. Then you can easily ask them to give you or supply you with the request ID, like for a sample request which failed for them, and then you can use that to start your investigation, which is great. You don't want, the worst thing that can happen is your user says they're getting a 500 internal server error, and you have to use the timestamp to find out logs from each service as to figure out what was going on. And I have a demo. So let's play it. Just going to resume it so that the quality is better. So this is in this repository, which I mentioned at the top. So logging WSGI, I run Docker Compose up, which brings up this bunch of containers. And you can already see these logs. They're already JSON formatted. They're from Junicon, and they're already JSON formatted thanks to Python JSON logger. Then we make an example request using curl. Sorry, yeah, that's what's at the bottom. So this is a better version. So you use curl to make an HTTP request to service 1, and this is supposed to be an HTML table. And then you go back to that console, and you can see this request IDs being logged. They're JSON formatted, which is great. You can also see we see some logs from the HTTP request client as well. That's because we have got the logging level set to debug somewhere at the beginning of our service. So that's great. Let's see. We add the verbose flag, and you can see that we have the X request ID sent back to us as a response header. And Of course, as you'd expect, it matches with the one that was generated here, so which is excellent. And that's it for the demo. Let's continue. Yep, one moment. All right, so let's move on. So the key things to log, that's always a question that you want to ask yourself. What should you be logging? Of course, for HTTP applications, some of the most basic things that come to mind are the request path method, the content type, perhaps. For those edge cases where your user is not setting the right content type and they get a weird HTTP error instead of, say, a bad request, they might get 500 or I don't know, even worse. So you'd want those key things to be logged. Response status, very useful to figure out what may be happening with a request. And then we have exceptions, of course, expected exceptions especially, and again, you would want to leverage the HTTP middleware for this to ensure that your exceptions are logged and it has a request ID set along with it. Those are probably the most useful ones to be logged, the unexpected exceptions. And then generic things to log, even if it is not an HTTP application, even if it's an RPC service, is version identifier, some way to correlate the running version of your application to the code that the version of the code. Git commit hash is a useful identifier. Some way to tie the build and deploy pipeline, so maybe a deployment ID to your logs. That will be useful as well. Sampling may be useful, especially in verbose logging situations, but it can be a slippery slope. Don't sample error logs if you're sampling at all, because especially for those one-off things that only get reproduced once or 5 times among your 1,000 requests, you don't want to lose that due to your sampling. Some generic strategies around logging: decouple log processing and output selection from application. What I mean is, your infrastructure may have Elasticsearch as your logging storage, or it may be using something else. Your application shouldn't need to know that. Always log to standard out. For those among you who are familiar with the 12-factor app methodology, this would be one of those things that you want to always make sure that you're following. Your application shouldn't be coupled to where your logs end up. You should always log to standard out and let the logging pipeline and sort of take that log from your application to that final storage and indexing mechanism. Use log forwarding solutions, FluentBeat, FluentD, Logstash. These solutions allow you to implement log processing pipelines. So if you wanted to add a metadata or remove a metadata, you will do it here rather than doing it in your application. FluentBeat also has this stream processing engine, which lets you run SQL queries on your logs, which means more ways to process your logs. And again, focusing on not doing this in your application. Make your applications as dumb as it gets when it comes to logging, and let the other stuff happen outside the application. All right, next we move on to metrics. What is a metric? It's a number representing your system behavior. Past few years, another term has been more popular, which is also referring to the similar thing as far as my understanding is concerned, and that's a service level indicator, SLI. You may be hearing this a lot these days. Essentially, yeah, if your web application, if it's a web application, you want to know how many requests are failing, for example. That's a service level indicator. for your application. Why would you want metrics? Various reasons. You want to know when something is wrong, which means you want to be able to create some kind of alerting mechanism. You want to have auto scaling of your application instances, specifically horizontal scaling. You want to be able to set expectations of your service, such as which are usually formalized using service level objectives, and more. And when you're talking about money, service level agreements. You don't want to aim for 100% or even 5.9 livability when you don't need it, right? Your customer may not even need that. So why set unrealistic expectations? But also to understand what is your behavior, what is your availability. So it essentially helps you answer these questions. Now, of course, what should you be monitoring for HTTP RPC server applications? Response status, request latency, uncaught exceptions, your health checks, whether they are passing or not. Because if your health checks are not passing, then your application is not ready for serving your customers. If you are using it's very likely that you're not just using a web application. You're probably also leveraging some kind of asynchronous worker processes, such as Celery, which is very popular in the Python ecosystem. In those, for those applications, you would want to task processing latency, but it can be tricky, as you probably know if you have tried it. Distributed tracing, which is the next topic, may help here. Task processing errors is something that you definitely want to know. If your worker is pulling a message of a queue and it's not working and it's not succeeding, you'd want a way to track that. Queue size, if your workers are all overloaded, or worse, if they are or all down, you want to know. And monitoring the queue size is a good way to know that whether your workers are up and running or not. An alternative strategy, or maybe a more foolproof strategy, in addition to the queue size, is also having health check for workers. Now, you may want to implement like a HTTP sort of listener to monitor the workers, or it may be another way to do it, which is look for the process name and see if they're alive or not. Again, the strategies will vary depending on your exact work application, but the idea is to have a way to know when your workers are not functioning correctly. Things to keep in mind, not all monitoring solutions out there, Prometheus, for example, are suitable to WSGI's multi-process model. It's just an unfortunate situation when to find yourself in when you learn all about this shiny new great excellent open source tool, and you try use it and you find that it's not very suitable for your WSGI multi-process application due to the sort of premise of Prometheus, which is like a single process but multi-thread model, which is not WSGI's model. As we'll learn later, StatsD is useful here. We can still leverage Prometheus, but we need to have like a bridge in between. And of course, the ASGI async IO application for ASGI async IO applications, not all monitoring solutions and libraries still support it fully. So you will need to do your research before you choose one. However, I've had quite a bit of success using Prometheus directly with AIO HTTP applications, which means at least theoretically it should work, whether it scales in production or not, because you may not be able to handle all your traffic with a single process, for instance, of your application. So yeah, your leverage, your mileage may vary. All right, next we have distributed tracing. What is distributed tracing? So the basic idea is a single user operation can involve call to one or more services, a database call, and a bunch of other stuff. Let's refer to each of these things as contexts. So latency metrics, if you have implemented metrics, latency metrics, for example, give us visibility into each individual context. but not the whole picture. Distributed tracing aims to give us that visibility into this whole picture. How does it do that? It essentially it gives us a mechanism. It allows us to implement a mechanism where we are able to propagate this operational context across services. It's similar to the request ID. It's usually referred to as a trace ID in distributed tracing world. It bridges the gap between responsibility and control. If that sounds cryptic, that's because it's taken from this excellent write-up on this topic around deep systems, how in today's microservice architecture, you may have the responsibility of a service, but you are not really in control of all the dependencies. Sorry, let me rephrase it this way. You are responsible for a service, but you're not really in control because your service relies on this other 10 other services to do its job. And that's what the author refers to as deep systems. And that's where distributed tracing helps massively, because then you get visibility into the performance of not only just your service, but what's happening with this other services that you rely on. And it's also useful for asynchronous task latency tracking. Okay, now how do we go about implementing metrics and distributed tracing? You need to instrument your code. Of course, you plug in code to export monitoring data, export trace. And how do you do that? You use libraries. If you look around, you will find a lot of vendor-specific libraries. Honeycomb, one of the pioneers in this distributed tracing space, as far as I can recall, where they really sort of did a lot of work. They're still doing a lot of work in just developing this knowledge and know-how and expertise around observability in general, or Datadog, for example, or New Relic. They all have vendor-specific libraries, and you can use those to instrument. However, you may be wondering, or you may wonder when you evaluate the solutions, right? What if tomorrow I want to change my vendor? What if I'm not happy with these guys? What if the pricing is not really the most efficient for me? Well, the answer now, and even though it's a very much an in-progress effort, is OpenTelemetry. This project is aiming to come up with vendor-neutral libraries for metrics as well as distributed tracing. Now, instrumentation is just one part of the implementing monitoring and distributed tracing. You need specialized storage for time series data. You need a specialized query and calculation engine. For traces, you need specialized query and visualization capabilities. Traces is interesting because some general purpose storage are also useful here. Like some tracing systems allow you to use SQL databases, Elasticsearch, and others. There are a few alternatives, as you can imagine, when you go to implement these things in practice. OpenTelemetry. So it's a vendor-neutral specification and SDKs for logging, monitoring, and tracing. It's a combination of two projects, which were called Open Census for metrics and Open Tracing for distributed tracing. Logging is not yet available for Python, but that's okay because we're only logging to standard out. So we are not really, going to, use any vendor libraries anywhere, because we are not going to send our logs directly to a vendor. We're going to send logs directly we're going to send logs to stand out. So that's okay. Don't need to worry about it. OpenTelemetry also gives us automatic instrumentation libraries for tracing, as you'll see later on. So just to clarify what the promise or what OpenTelemetry really gives us. So before OpenTelemetry, your application would use a vendor, specific library to emit the metrics, to emit the traces. And this would be, say, maybe sidecars in your infrastructure, or this may be directly sending it to the vendor. So Splunk is a popular vendor for logging, SignalFX is a vendor for metrics, and Lightstep is a popular vendor for distributed tracing. So you directly, send those data into their, custom vendors. After OpenTelemetry, however, you suddenly have this vendor neutral situation where you're using a vendor neutral library here, you're using a vendor neutral, probably an agent or a sidecar here. And then this OpenTelemetry collector is also another vendor neutral component. And then finally, at the very last step is where you have this vendor specific components. So if tomorrow you wanted to switch out Splunk for Elasticsearch, maybe you just need to change this bit. And similarly for the others, which is really exciting. All right, let's see how we can instrument our WSGI application for Matrix. I said we are not going to use OpenTelemetry. I said we can't use Prometheus for WSGI applications, and that's the main reason we can't use OpenTelemetry for WSGI applications. Please see the Git repository for a brief explanation and detailed links to some other resources I have on this subject. So what we're going to do today in our demo, or I believe is the only way you can use Prometheus from your Python application, is have this open source project called statsd exporter running. And then from your application processes, which is WSGI, UWSGI, or Gunicon process, for example, you push your matrix to the statsd, and then Prometheus pulls data from statsd. So that's how your architecture would look like. How would the instrumentation exactly be done? Again, this is an application from Flask. The ideas are going to be very similar for Django or other web framework using. So we have two functions. So this is specifically for tracking the latency of a request. So we have a start timer. We start this timer here. We again use the request object to store this time. And then you have a stop timer where we just before sending the response back, we calculate the current time and we access the start time using this object. And then we, using this vendor specific library called statsd, or it's a Datadog, it's a library given by Datadog, open source library by Datadog. We push this metric to the statsd exporter. Now, of course, as you can see, the vendor neutral bit sort of breaks down here. And that's because we cannot use OpenTelemetry for Python instrumentation yet. And then we have the Flask app instrumentation. So this is how we could, this is another function which we use to record, a counter request data. So this is another metric we are tracking. This tags that you see here, these are metadata that we attach to this metric. And finally, we use this, we register those functions using the middleware functions here. So before request and after request for registering those functions. And as I mentioned in one of the earlier slides, we should also export metrics from the WSGI runtime. And this is an example for Gunicon, where you just specify the statsd host, and that will push statsd metrics from Gunicon. You can do something similar for UWSGI as well. And these metrics are, sample metrics such as worker metrics, the request statistics are pushed. Let's see a demo. So what I'm going to do is I'm going to just, let's do full screen. So again, the same repo, we go into the directory matrix WSGI, we run Docker compose up. I have set this up so that there is a script that's using Apache Bench to make a lot of requests. No, sorry, that was from the wrong demo. Ignore that. So you're just going to make some requests manually here. And as you can see, those logs, and then if we into our browser, we go, so this is Prometheus. If you go into localhost 9090, that's your local Prometheus installation. And these are the metrics that Gunicon gives us automatically. So you can see this here. we pushed some sample metrics on our own. Request latency seconds. This is one we push, and you can see that you have this endpoints on which the request came in. You can see that there are two tags here: service 1, service 2. And as you recall, we have got two services running here. So that's how we can get metrics easily. All right. Let's continue. Oops, sorry. Pointer. Okay, let's move on. Okay, next we are going to look at open telemetry using. So for tracing, we are going to use open telemetry, which is great. The open telemetry libraries are perfectly usable with Python, and so we're going to use that. So I'm not going to go over in detail what these statements mean, but this is how you initialize the open telemetry, sort of machinery. Key things here are this endpoint. So this is where the tracing data would be sent to, and this is the component is called an open telemetry collector. So it's going to send it here to this endpoint, which I've got configured on in a Docker container. Insecure equal to true, of course, we're not using TLS verification here. But the key thing, so if you then sort of think about how do we get this instrumentation? So I mentioned automatic instrumentation. So already OpenTelemetry has libraries for automatically instrumenting your Flask application. And all you do is pass your app instance to this. Similarly for requests, which is HTTP request library, and MySQL instrumentation as well via this other library. But that's automatic instrumentation. How do we create manually? How do we instrument our code that we are writing in our application? This is how you do it. So this snippet is from service 1, and this is where we are calling service 2. So what I do is we create a context using this context manager. We name this current span as service 2 request, and then I call service 2. And that's it. Similarly, in service 2, when you're making a database query, we start this service 2 DB context, and then we run our MySQL, usual MySQL stuff. We connect to the database, we queries, and do all that stuff. And that's how you create spans. And you automatically get this traces propagated. Once again, we are going to our repository. We'll go into the distributed tracing. We'll start the compose up. So yeah, so in this Docker Compose file, I have got this other container, which uses Apache Bench to make a bunch of requests to service 1. And we'll see that start in a bit. Yeah, so you can see all these requests that it's making just to, sort of simulate a scenario where you have a lot of requests coming in. So, all right, so the requests have completed. Now, if you go into this URL in your browser, so this is a specific distributed tracing engine, I want to say. It's called Jaeger. It's just one of the solutions that you can use to implement store your traces in. So this is a storage and querying system for distributed tracing. And you can see that you automatically, so I'll pause a bit, you can see that it already gives you some interesting data that it shows you this dependency. Imagine if you had 10 other services, you could easily see this visualization. All right, let's continue. And then when you click on view traces, you can see all these bits. And you can see the 6 spans. And if you click on one, you can see this entire call hierarchy almost. So let's pause there a bit. You can see that first we had service 1 making this call to service 2, service 2 getting this call, and then it making this query to service 2, the database. So let's play on. So if you click on any, you see more information related to that. And then eventually you can see that if you click on that SQL select statement, you can even see the latency metrics related to that query itself. How useful is that going to be in your production scenario? I can only imagine that you're getting very excited. And you should, because I really got excited when I first started exploring this. So let's continue. I have a feeling I'm running short of time. I'm not timing it. Quite dumb of me, but I'm going to skip for these 2 slides. All right. Now, what if the demonstrated implementation is not suitable for your production infrastructure? Maybe you don't have the right tools in your infrastructure. Maybe you're stretched for time. Consider using a SaaS vendor, Honeycomb, Datadog, New Relic, Lightstep. All of these vendors will probably have almost all of these features, but if they don't, the key idea that I want to give here is that don't sweat on that, because what I want you to know is don't ship your code with instrumentation. Logs, metrics, traces, you will need them. Let me go back here. Now, you might think, okay, but how do we get all of these without, for the least effort possible? Well, for metrics, you'll most likely see that if you run an agent along with the application, you will get a fair bit of data out of the box. You wouldn't need to do manual instrumentation in your code for metrics, which is not a bad place to be. You can start off with that. However, for distributed tracing, your code will need instrumentation because you need to propagate the trace IDs. One suggestion is go with the vendor which is compatible with OpenTelemetry, since you don't get the lock-in. I suggest searching for OpenTelemetry with your vendor. So, for example, Honeycomb has an OpenTelemetry support completely. I believe other vendors would also have that. But do your research before you decide to go with that vendor. All right. That brings to my second part of the talk, which is on resiliency. There are multiple facets of resiliency. We are going to take a look at only a few. So the first thing I want to talk about is horizontal scaling. Especially with cloud providers, container orchestrators such as Kubernetes, you can set up the infrastructure to say, hey, if this metric goes over this, or increase the number of instances of application. In most cases, you will, of course, this only applies to web application instances or worker processes. Again, your metrics will become useful here, your CPU usage, your requests. Look for patterns, any metric, any SLI that has a correlation with positive correlation with your request, or even a negative correlation for that matter, with your traffic, that's the metric to go for. So that's the idea. Simulate failure scenarios. You may have been hearing about this new relatively new area called chaos engineering. I highly recommend this resource called Principles of Chaos Engineering before you understand what chaos engineering is, so that you understand what chaos engineering is all about before you look for a tool to implement chaos engineering. Some experiments you can run is inject latency into calls to dependencies. It tests your timeout behavior. It tests your error reporting and alerting. Terminate an instance of application randomly, which is what Chaos Monkey by Netflix started off as. It tests your auto-scaling behavior. Get creative. Terminate your worker processes for whiskey runtimes. Fill up disk space and observe what happens. Of course, don't do it directly in production. Start off with your staging test environment, and then think about how you can run these experiments in production. Other important things: rate limiting. You've got to protect your services from intentional, unintentional, malicious behavior. Circuit breaking, reduce the blast radius. Service meshes may help here as well, because they automatically come up with, sometimes have these features, which means you as an application developer don't need to worry about implementing those in your code. All right. So summary: your service will fail badly at some point of time for some reason in some capacity. That's just the nature of running internet services. But you want to be ready for it. You want to have the tools so that you know how to debug. You know how to where to look when things are not going the way you would want them to. Focus on observability of your service from the get-go. Structured logs, metrics, and traces. Run regular chaos engineering exercises as an exploration of your services production readiness. I approach chaos engineering exercises as with a curious mind. I want to know, hey, when I do this, what's happened? Are my dashboards, are my metrics telling me what's going to happen, or what's happening? So a bit of curiosity is correct for chaos engineering. And then, of course, implement resiliency patterns. It may feel like a lot of work to start off with, especially when when your services are not falling over. But you don't want to be reactive. It's always good to be proactive. All right. Thank you for attending my presentation. If you have any questions or comments, please get in touch on Twitter or my email address. These are the demos and resources. Yeah, thank you. I hope you enjoy the rest of the conference.